Welcome to the third lecture of nonlinear modeling. Today, we are going to finish geometrical nonlinearities. We'll start with a recap of what we've talked about last week. Then I'll talk about the second P-Euler culture of stress on a truss, because this turned out to be the most difficult concept to grasp. Afterwards, I'll move on to the finite element discretization of the wake form, and I will give examples of the tangent stiffness matrix, in particular the geometric stiffness matrix, for a few structural elements. And then I'll end a geometrical nonlinearity chapter with linear buckling and post-buckling analysis. Last week, in the part 1 of geometrical nonlinearity chapter, we've talked about the descriptions of kinematics, statics, and we've derived balance laws in strong and weak forms. Under kinematics description, we've developed the concepts of the deformation gradient, and we've come up with a nonlinear strain measure, which is the Green-Lagrange strain tensor. Under statics, we've developed the first P-Euler culture of stress and the second P-Euler culture of stress. And we mentioned that the second P-Euler culture of stress and the Green-Lagrange strain, they are natural pairs for each other in terms of constitutive laws. So in practice, we calculate the Green-Lagrange strain tensor based on the deformation. So here the deformation gradient and the displacement field. Then we apply the constitutive law, the equations of a constitutive law, and obtain our second P-Euler culture of stress. The product of the first P-Euler culture of stress with the normal of the surface, dA0, in the initial configuration, gives us the engineering stress, which is dF, which is the actual force applied on this surface, over dA0, the initial area of this surface. While for the second P-Euler culture of stress, its product with the surface normal in the initial configuration gives us sort of a pullback traction, so it's not the engineering stress, and this quantity equals dF0 over dA0, where dF0 is a pullback of dF, and I said that this is artificial force, so imagined quantity to facilitate the development of this second P-Euler culture of stress tensor. Then we've derived the balance law or the equilibrium equation in strong form, and we subsequently derived the balance law in the weak form, which is the equivalent to the Waterwork principle. On the left, we have the internal Waterwork expressed as the integral of the variation of Green-Lagrange strain tensor in the product with the second P-Euler culture of stress tensor. On the right, we have the external waterwork done by the body force and the surface traction, respectively. Here, B0 is the body force density in the initial configuration, and T0 is our engineering stress, so it equals to the actual force divided by the initial area. So across all these quantities mentioned on this slide, probably the second P-Euler culture of stress is the most difficult to grasp. All the rest are relatively easier to understand. So I would like to demonstrate the second P-Euler culture of stress on a simple example of a truss. Now we are going to analyze this truss in a small strain, large displacement assumption. So it's still geometrically nonlinear, but we consider that the truss is quite rigid and it doesn't change much in terms of length or cross-section, which means that under loading it may move and rotate, but its length and cross-sectional area L and A, they are pretty much the same as L0 and A0. So the normal N, the current normal N, would rotate, but as I mentioned, these quantities remain roughly the same. I would like to demonstrate the second P-Euler culture of stress components on this simple example. So now, since we've mentioned that the length doesn't change much, so our deformation gradient after polar decomposition remains only the rotation R. And the determinant is approximately 0 because we are not changing much the volume. And then if we calculate our first P-Euler culture of stress, we have the determinant of F roughly equal to 1, and the F inverse transpose would be roughly equals to rotation R. And then we are left with tau, which is our Cauchy stress tensor, multiplied with R, our rotation matrix. Then we calculate the second P-Euler culture of stress, which equals F inverse times P. And since F is roughly just R, and the R is a rotation matrix, its inverse is its transpose, so we can obtain that S, our second pure cultural stress tensor, being roughly R transpose times tau times R. So some of you may be already familiar with the expression. This is just the rotation of the stress tensor with R transpose. And you get the same formula if you just do stress rotation. You should have come across this concept of stress rotation in maybe second or third year of mechanics course, where we talk about principal stress and principal strains. There we do a similar rotation to obtain stresses along the principal axes. And let's calculate the components. Right? So let's say I want to find the relationship between the component along the normal direction, tau n, which is our true stress or Cauchy stress along the normal direction in the current configuration, with the component of S along n0 along the normal direction in the initial configuration. We can see that if we apply a series of calculations, so tau n is n transpose times tau times n. This gives us the component of stress along the normal direction. Then because n is R times n0, we pre and multiply with this formula. And because R transpose tau R is now approximately our S, we obtain this formula. And this gives us the component of S along the normal direction, n0, in the initial configuration. So you can see that these two are pretty much the same. So what does it mean is that now I have, let's say, my true stress along the normal direction. If I multiply the tau, my Cauchy stress, with the normal n, now I consider the pullback of P as applying the inverse of F on the actual force P times n. P is magnitude, n is the normal. So I get my P0, N0. So this is the pullback force that we talked about in last week. And this is roughly equals to R transpose P, because F inverse is R inverse, which is R transpose. Now, P is a scalar. I can bring it forward. R transpose times N. If I apply this formula, gives me N0. So you can see that on the left side, P0 is approximately the same as P. What it means is that I'm just simply rotating this P onto the N0 axis, and this is what the pullback is doing. Now if I calculate the S times N0, which gives me the second pure curve stress along the normal direction N0 on the surface with a normal N0, I would obtain, according to what we learned last week, it should be equal to P0 over A0, and since P0 and A0 are approximately equal to P and A respectively, we obtain this formula. Right? And then you can see that this P over A is a magnitude of the stress along the N0 direction, and P over A is a magnitude of the Cauchy stress along the N direction. They are the same. So this means that if, let's say, I calculated my second pure curve stress from my constitutive law through the Grignard-Lagrange strain tensor, and I obtained the stress components around the normal or transverse directions respectively in the initial configuration. Under the assumption of small strain, I can pretty much say that the normal and transverse stresses in a deformed configuration, the true stresses, are of a similar amplitude as the one that I have in the initial configuration. Okay, so they are just being rotated in terms of direction, but the magnitudes remain roughly the same. Of course, once we remove the small strain assumption, the magnitude will also change, so it would scale with respect to your change of area and length. But most of the case in aerospace applications, we are concerned with small strain large displacement analysis, and this should apply.